Okay, today, or the purpose of this video, is to go give you the rest of the solutions to the even problems, as well as make sure to try to clear up some of the confusion on some of the higher order stuff, particularly with quantum numbers and some of those. Now, the first even one I had not given you a solution to yet was number 40. But when you plug and chug, your answer should have come out to been for the wavelength 3.01 meters. Okay? And that's where we would have solved that one. All right, the next thing that I want to do is jump up to 68 and 69. But before we do that, I want to come back to our diagonal diagram because I think that this will give us the perception of how we need to use this to help solve that problems and where the answers come from. Now we know that we can use this as a way to determine the order of the electrons, but if we come back and look at it from an energy level perspective without the overlap, just as a reminder, in the first energy level you would have a total of 1 orbital and 2 electrons in the 1s. That's it. Okay? Now for the 2s, if you remember, if you look at orbitals, you can square it, so there would be 4 orbitals and a total of 8 electrons, which also, just as a reminder, if you look on the periodic table, well, if you add up your, this isn't going to probably let me write on this. We'll see here. No, okay. If you add up the 2 and the 2s, 1, 2, and then 3, 4, 5, 6, 7, 8, well, that makes sense. There's your number of electrons and your number of orbitals. So 8 total, 1 orbital for the s's, 3 for the p's. Now the 3's, we add in the d, so that's why we end up with 9 orbitals, 3 squared, which leads us to 18 electrons. Again, the difference between 8 and 18 is the fact that we added the 10 in the d block. The 4, again, if you take 4 and you square it, you've got 16 total orbitals. That's going to be from the 4f, because if you add 7 to 9, you're going to get 16 orbitals and 32 electrons. Now, if you look at 68, if I do this in the context of this, just to give you the right answers for these, what it's asking you in 68, I'm going to kind of jump back and forth here for a second, but what it's asking you is how many electrons in an atom can have the following designations. Now, we know that 1p is going to be 0 because there is no 1p orbital. We can't ever go up further than that, okay? Now, when we get to the next one where it has the 6 d x squared minus y squared. What we're going, the only difference here is, now we know that there's a 6d, it's on the chart, but the fact that they gave us that subscript is telling me which particular d orbital that it's talking about. So for this one, it's only going to be 2 electrons. Now just to kind of show you where that comes from is, again, if you think about it, and one of the leaps we're doing this year, I'm going to scroll back and forth here a little bit, is with that third quantum number. We know the first one gives us the energy level, second one gives us the shape, the third one gives us which designation. So for the s's, the reason it's equal to 0 is because there's only 1. And for the p's, you've got -1, oops, that's not what I wanted to do. Make this a little bit bigger here. For the p's, you have 3 of them, which could be -1, 0, and +1, which we also this year can refer to as px, py, and pz. I think the expanded form is what Shakashiri did. Now the d's, there are 5. It's going to go from -2, -1, 0, I did it again, +1, that one's not higher, I just don't want to erase it again, +2, and then finally for your f's, you've got -3, -2, -1, 0, +1, +2, and +3. So when it's telling you, way back up here, the 6 dx2-y2, well, the chart that I need you to copy down, I think it's on page 310, all the different shapes, that's just telling you which specific d orbital. So that's why it's only going to be 2 on that one. Now, if you look at the next one, if you look at 4f, okay, 4f is looking at all 5 of the 4f orbitals, and so since it's asking about electrons, sorry, all 7 of the 4f orbitals, so since you're looking at 7 orbitals for 4f, it's going to be equal to 14 electrons, Okay. The next one after 4F is 7py. Again, that comes back to this orientation right here, where it's just telling you which one. So 7py is also going to have 2 electrons, right on the edge there, just like the 6dx2 minus y2. Okay, so 2s is also going to fall into this category of having 2 electrons. Let me separate that out a little bit. And then finally you've got n equals 3, which we talked about right here, which could be 18 electrons. Okay, so there are the answers for that one, for n equals 3 for 68. Now, if you look at 69, it gets a little bit, kind of takes us to the next level, so to speak. But if you look at 69, I'll at least explain the first 3 of them. It's 69 says give the maximum number of electrons in an atom that can have these quantum numbers. Okay, so if you look at n equals 4, okay, we've already done this. If you have n equals 4, you take n squared, multiply it by 2, so you get 32 electrons for n is equal to 4. Now for the 5s, if you think about it, in the past, right, if we do n squared, we get 25 orbitals for 5s, and which means a total of 50 electrons. Now if you look on this diagram, there's no additional set of orbitals, but the reality of it is if remember, each time we come down an energy level, we add another option for orbitals. So if we follow the same pattern, and most of the time we refer to it as a G, I'm not sure why, it's just the one after G, but if it was G, and there's 1 in the S's, there's 3 in the P's, there's 5, that's not what I want to do. There's 5 for the D's, there's 7 for the F's, it would be 9 orbitals, which if you think about it, there's the gap between. Okay, so what happens is that extra 9 orbitals that get added for the G bridge the gap between 16 and 25, and then if you add the 18 electrons, well, that bridges the gap between 32 and 50. Okay, so if you look at 69b, it wants to know how many maximum number of electrons can be in n equals 5, but an ml value of +1. So I'm going to, in order to explain that, I'm going to come back down to our little drawings we did earlier for the ml numbers, because if you think about in level 5, there is a 5s, but none of them have a +1, so there isn't one for the 5s, but the p's, there's one that has a +1. So there's 2 electrons that are in the 5p that can have a +1. There are 2 electrons in the 5d because one of the d's can have a +1, and there are 2 electrons in the 5f because 2 of the f orbitals can have +1. And if we get to that, in theory, that level G, well, the G third quantum number levels are going to go from -4 to +4, and there's going to be one that has +1, so it's going to be 1 up and 1 down, which means that for 69b, for the ones that have n equals 5 and ml of +1, it's 8 electrons. Okay, 8 electrons is going to be the answer. Now, if you look at 69c, it's kind of a similar pathway. You got to use that hypothetical electron G sublevel. If you look at the fact that in the 5th energy level, we can have a potential for 25 orbitals and 50 electrons. All right, which is not totally foreign. Well, if we think about that, every one of those 25 orbitals is going to have an up arrow that we usually attribute to +1/2 and a minus arrow, a down arrow, that we usually attribute to -1/2. So if you look at 69c, where it's saying n equals 5 and +1/2, that's where they get the 25 electrons, because they're only taking the electrons that have that +1/2 value. Okay, and then hopefully you can figure out D and E on your, or understand the rationale for that on the way down the thing. Okay, 82 we did in class. Remember 82, this is just a reminder that the answers to 82 were letter A. Here was the excited version. Remember, an excited version is just anything that is not typical. It does not follow the Aufbau principle. It does not follow the lowest to highest energy. This would be the accepted value, the accepted for 82. For C, we're dealing with fluorine. Here was the excited version. This is what they gave you in the problem. And again, it's excited because it didn't completely fill the 2p before moving on to 3s. This is the expected, and then D was also the other correct answer for that one as well. B was not correct, was not an excited state because it follows the Aufbau principle. Okay, the last ones that I want to talk to kind of go together, and they are number 90 to give you the solutions, as well as number 93 to try to attempt to explain what that means. Now, if you look at number 90, for number 90, it wants to know the smallest ionization energy of everything in that group. And so for 90A, let me get to the right page here. Okay, the correct answer for 90A actually follows the typical pattern, and it's going to be barium rather. Okay, follows the pattern. Letter B, the same way, it's going to be potassium. Now we get to letter C, and this is where our exception for ionization energy comes in. I kind of didn't tell you all the truth last year. There is a exception for 15 versus 16 on this. And if you need a little bit more detail, if you go to page 326 in your textbook, you read that middle paragraph, it's going to explain that hopefully maybe a little better than what I can if you don't follow me. But if you look on page 326, if you look at letter C, 90C, they're looking at the difference between nitrogen, oxygen, and fluorine. Now, if you just look at the numbers, it doesn't follow the expected pattern, right? Nitrogen is 1,402, oxygen actually dips down 1,114, and fluorine goes back up again, 1,681, and just as a reminder, fluorine is the most electronegative, so that's why it's got one of the highest ionization energies except for the noble gases. Okay, so we would expect it to be nitrogen, but that's not the case. And why is that? Well, it all comes down to those electron configurations. The electron configuration for nitrogen, right? If we do the px, py, pz, this is 2p. There's 3 of them. 1, 2, 3. So each one of those p's only has 1 electron floating around. Well, when you get to oxygen, px, py, pz, you have 1, 2, 3, and then 2 electrons. Now, if you remember correctly, electrons are still all negatively charged, so they still repel each other just a little bit. And the fact that these 2 electrons are both in the same orbital provides enough repulsion force, and remember repulsion is going to push them away from each other, to actually lower the ionization energy. So if you look at the chart on the bottom of page 326, you'll see it's a pretty regular exception for the 15s versus the 16s, and it all comes down to this electron repulsion. If there's enough repulsion, it's going to lower the amount of energy required to remove an electron. Okay? So hopefully that helps on that one. Now if you look at 90D, we have 3 versions of the sulfur atom. You have the sulfide ion, you have the sulfur ion, and where you happen to be able to get it to rip off 2 electrons. Now, another way to think about this, the correct answer for this one, okay, should be the actual sulfide ion. And again, it comes down to the repulsion. If you think about the sulfide ion, here's my periodic table, the sulfide ion has gained 2 electrons to be happy and to be like argon. So if we come back over here, if we think about the electron configuration, we've got 1, 2, 3, 4, 5, 6. Now you may think, oh, they're happy, so they're not going to want to let go of any, but that's not the case, because every time you add an electron, the noble gases are solid because they've got the same number of protons and the same number of electrons. When you add an electron, all you're doing is you're still increasing the repulsion because you've now paired these last 2 up and now you have some increased repulsive forces. So of these 3 options, the sulfide is going to, even though it's happy and it's got its noble gas configuration, it's still going to be the most willing to give up electrons more so than the other ones. Okay? So that's the explanation on that one. And then letter E, 90E, goes back to following the regular old pattern. 90E is going to be cesium. Okay, and if you look at 93, that's kind of the explanation for what we're going for 93 as well. In terms of electron configurations, when you're dealing with arsenic, and selenium, it's the same deal as nitrogen and oxygen. So although the answer in the back of the book is wordy, it still all comes back to this repulsion and the fact that the group 16s, your oxygen and your selenium, this repulsion and driving them away from each other lowers the ionization energy just enough. Okay. So hopefully that helps. If you have any other major questions, shoot me an email and I will try to get them answered and get a video out to you.